An anode and cathode are fundamental concepts in the field of electrochemistry and electronics, representing two types of electrodes used in various applications, including batteries, electrolytic cells, and electronic components. Here is a detailed explanation of each. Anode, the electrode where oxidation occurs. Electrons are generated at the anode and flow out of the device. Cathode, the electrode where reduction takes place. Electrons flow into the cathode from the external circuit, leading to a reduction reaction. Sodium oxidation refers to the process in which sodium, Na, loses electrons to form sodium ions. This reaction can occur in various environmental and chemical contexts, particularly in redox, reduction oxidation, reactions. The reduction of chlorine, Cl, to chloride ions, Cl, is a fundamental redox, reduction oxidation, reaction that occurs in various chemical and environmental processes. This transformation is significant in chemistry, particularly in the realms of electrochemistry, environmental science, and industrial applications. The rate of electron transfer in redox reactions between molecules A and B is influenced by molecular size. Larger molecules often exhibit slower electron transfer kinetics due to increased distance between redox centers and hindered diffusion, impacting the overall reaction efficiency. Redox reactions involve the transfer of electrons from a reducing agent, species A, to an oxidizing agent, species B. This electron transfer results in a change in oxidation state for both A and B, with A undergoing oxidation, electron loss, and B undergoing reduction, electron gain. The transfer of an electron from molecule A to molecule B results in a demonstrable alteration of the respective molecular geometries. Specifically, molecule A, upon relinquishing an electron, transitions to a cationic state, A. This cationic species exhibits a reduced atomic radius compared to its neutral precursor due to the diminished electron-electron repulsion within its electron cloud. The effective nuclear charge experienced by the remaining electrons in A is consequently increased, drawing them closer to the nucleus and thereby contracting the overall size of the ion. Conversely, molecule B, having accepted the electron, becomes an anionic species, B. The addition of an electron to molecule B increases the electron-electron repulsion, resulting in a greater spatial distribution of the electron cloud. This expansion of the electron cloud leads to an increase in the ionic radius of B relative to its neutral counterpart. Therefore, the electron transfer process manifests not only a change in the charge states of the involved molecules, but also a measurable difference in their respective sizes, with A experiencing a decrease and B experiencing an increase. The reaction between zinc, Zn, and copper, 2-sulfate, CuSO4, is a classic example of a single displacement or redox reaction, wherein zinc, possessing a higher standard reduction potential than copper, displaces copper ions from the solution. Specifically, zinc undergoes oxidation, transitioning from its elemental 0 oxidation state to a +2 oxidation state, forming zinc ions, Zn superscript 2. Concurrently, copper, 2, ions, Cu superscript 2, in the copper, 2, sulfate solution undergo reduction, accepting electrons and reverting to their elemental 0 oxidation state, precipitating out of solution as metallic copper Cu. This process can be represented by the balanced net ionic equation, Zns plus Cu superscript 2, Aq, Zn superscript 2, Aq, plus Cus. The driving force behind this spontaneous reaction is the difference in the reduction potentials of zinc and copper. Zinc's greater tendency to lose electrons compared to copper ensures the thermodynamic favorability of the electron transfer. The observation of a reddish-brown copper deposit forming on the zinc metal surface, alongside a concomitant fading of the blue color characteristic of the Cu superscript 2 ions in solution, provides visual confirmation of this redox process. The reaction's completion is indicated by the cessation of the color change and the cessation of any visible bubbling, should impurities in the zinc cause a secondary reaction with water. Furthermore, the stoichiometry of the balanced equation dictates the precise molar ratios involved in the reaction, enabling quantitative analysis of the reactants and products. An electrode is a substance that is in use for the conduction of electricity. The electric current comes or leaves the nonmetallic medium like an electrolytic cell. In simple language, an electrode is a conductor that helps in establishing electrical contact with a nonmetallic part of the circuit. Electrodes consist of two main things that are cathode and anode, which basically describe the direction of flow of current. The terms anode and cathode are not given by the voltage polarity of electrodes, but the direction of current through the electrode. Cathode and anode. What is a cathode? It is an electrode from which a current leaves a polarized electrical device. This can be recalled by using the mnemonic Cathode Current Departs. A conventional current shows the direction in which positive charges move. Electrons have a negative electrical charge. Therefore, the movement of electrons is opposite to that of the current flow. Example of cathode. The cathodic current is the flow of electrons from the cathode interface to a species in solution. Electrolytic cell. In an electrolytic cell, the cathode is where the negative polarity is applied. Some results of reduction at the cathode are pure metal or hydrogen gas from metal ions. While studying the relative reducing power of two redox agents, the couple for making the more reducing species is more cathodic with respect to the more easily reduced reagent. Galvanic cell. In a galvanic cell, the cathode is the positive pole. This positive pole is connected to allow the circuit to be completed. The anode of the galvanic cell gives off electrons and return from the circuit into the cell through the cathode. Electroplating metal cathode, electrolysis. When metal ions are reduced, they form a pure metal surface on the cathode. Items to be plated with pure metal are attached and become part of the cathode in the solution. Anode. An anode is an electrode by which the conventional current enters into a polarized electrical device. In contrast with a cathode, an electrode by which conventional current leaves an electrical device. A common mnemonic is anode current into the device. The direction of current in a circuit is opposite to the direction of electron flow. Therefore, the negatively charged electrons flow out the anode of a galvanic cell into an external circuit connected to the cell. In both a galvanic cell and an electrolytic cell, the anode is the electrode where oxidation reaction occurs. In an electrolytic cell, the anode is the wire with a positive charge. Anions tend to move towards the anode where they can undergo oxidation. Historically, the anode was known as the zincode. Examples of anode. In a discharging battery or galvanic cell, the anode is the negative terminal because it is where current flows into the cell. This inward current is carried by electrons moving outwards. The negative charge flowing in one direction is equivalent to the positive charge flowing in the opposite direction. The electrolysis of sodium chloride, a process of significant industrial importance, involves the decomposition of molten or aqueous sodium chloride, NaCl, using an electric current. When molten NaCl is subjected to electrolysis, utilizing an inert electrode system such as graphite or platinum, the process yields elemental sodium at the cathode via the reduction half reaction, 2Na plus 2E2Na, L, and chlorine gas at the anode via the oxidation half reaction, 2ClCl2, G, plus 2E. This straightforward process is uncomplicated by the presence of water and is the primary industrial method for sodium metal production. Conversely, the electrolysis of aqueous NaCl, a significantly more complex scenario, produces different products due to the competitive reduction of water. While sodium ions are still present, the reduction potential of water to hydrogen gas, 2H2O plus 2EH2, G, plus 2OH, is less positive than that of sodium ions, resulting in the evolution of hydrogen gas at the cathode instead of sodium metal. Simultaneously, at the anode, chlorine gas is still produced, as the oxidation of chloride ions remains energetically favorable. Consequently, the net products of aqueous NaCl electrolysis are hydrogen gas, chlorine gas, and an aqueous solution of sodium hydroxide, a process of substantial commercial value for the production of this crucial base and the industrially vital chlorine gas. The precise conditions, such as electrode material, current density, and electrolyte concentration, significantly influence the efficiency and product yield in both molten and aqueous electrolysis of sodium chloride. A fuel cell car's power block comprises several key components working in concert to generate electricity. The system's core is the fuel cell stack, which may utilize various technologies including solid oxide fuel cells, SOFCs, proton exchange membrane, PEM, fuel cells, or alkaline exchange membrane, AEM, fuel cells. These stacks electrochemically convert the chemical energy of a fuel, such as natural gas, into electrical energy, with water and heat as byproducts. The power block also incorporates an engine, often a small auxiliary power unit or APU, for starting and auxiliary functions, and a system for managing the flow of fuel, oxygen, and water, crucial for optimal stack performance and longevity. Efficient energy management within the power block is paramount for maximizing vehicle range and minimizing energy loss.